Alright, today we're going to be talking about the Weierstrass Approximation Theorem. We're going to be providing a proof and a little bit of insight as to why this is so important. Lovingly called a lemma in this slide, the Weierstrass Approximation Theorem states that for every k subset of Rn compact and f continuous function from k to r, if epsilon is greater than 0, there exists a smooth approximation function g from Rn to r such that the distance between g and f is less than epsilon for all x in k. This approximation function g, therefore, uniformly approximates f on the set k. Now, why is this so important? Well, the real question is, how is this not important? Because this shows up everywhere in analysis. It's one of the greatest theorems that I've learned in my short time in math. Picture a continuous function which could be jagged and just terrible to work with. For example, Brownian motion. And as long as this function's domain is compact, we're able to approximate the function arbitrarily well by a smooth function. So really just a beautiful, beautiful claim and something that is extremely important. As we'll see, the proof of the Weierstrass Approximation Theorem is actually constructive, so it actually gives us a way to build G from scratch, which is also extremely useful. Now I will note that this is very different from, for example, a Taylor series approximation, because a Taylor series approximation is an approximation of a smooth function by polynomials. Okay, and in fact we require the function be analytic for the Taylor series to converge. So that's a much weaker claim, because we're only approximating functions that are infinitely differentiable and even more so analytic. Getting into the proof, first, since k is closed, there exists a continuous extension f tilde from Rn to R of f such that f tilde restricted to the compact set k agrees with the function f. This is a completely non-trivial claim and is a result of a more general extension theorem called the Tietze Extension Theorem. Even the proof in finite dimensional Rn is quite difficult and non-trivial, and you can try to prove this on your own, and you'll see that although it seems somewhat obvious that you should be able to extend a continuous function from a closed set to all of Rn, the reality couldn't be more true. It's completely non-trivial to extend this function, but we're just going to take it for granted for now. Now set epsilon greater than 0. We're going to define the smooth mollifier function eta epsilon. Now C infinity Rn, this means it's a smooth function from Rn to R, and smooth meaning it's infinitely differentiable, so it has derivatives of all orders. Now we want eta epsilon to satisfy the following. First, its support should be contained in a ball of radius epsilon centered at 0. That means that eta epsilon is going to vanish identically outside of this ball. So everywhere outside of the ball of radius epsilon, eta epsilon should be identically 0. Secondly, we're going to require that the total integral of eta epsilon is equal to 1. This isn't stated, but we're also kind of presuming that the function is positive, okay? So, for example, we could take eta of x to be constant multiplied by the exponential of 1 over norm x squared minus 1 when the norm of x is less than 1, and 0 when the norm of x is greater than or equal to 1, where we choose the constant c to normalize the integral of eta. Such a function looks like this. It's graphed here. Now notice that at the endpoints of the interval -1 and 1, the function flattens out. This corresponds to the fact that it needs to have infinite amount of derivatives at -1 and 1, and since outside of the interval it's identically 0, in order for those derivatives to exist, they had better be 0 on the inside as well. And so turns out that if you look at the derivative of eta of x and you take the limit as x approaches 1 or -1 from the inside of this interval, you will always get 0. And that's essentially due to the fact that the exponential function is going to converge quickly to 0. the exponential of negative infinity, colloquially, is going to dominate any polynomial, which might try to, make it non-zero. Okay, so this function has derivatives of infinite orders at -1 and 1, and everywhere else. And not only that, but we should note that at the endpoints -1 and 1, the function is not analytic, okay? So a Taylor series would require that you have a Taylor series which approximates the function, or is identically equal to, converges to the function in some neighborhood of the point, okay? So in a neighborhood of 1, because the derivatives of all orders are 0, that the unique analytic function would have to be the 0 function. And since eta is not 0 anywhere inside of this interval, it is not analytic at those points. However, it is smooth and the derivatives do exist to all orders. Okay, finally we're going to scale eta. We're going to choose this eta epsilon, which is scaled on the outside by a factor 1 over epsilon to the n, and on the argument of the function is scaled by 1 over epsilon. So scaling the argument by 1 over epsilon ensures that the support of eta epsilon stays within the ball of radius epsilon centered at 0, as we require. And then this outside scaling by 1 over epsilon to the n ensures that the integral over Rn remains 1. Now we're going to consider the following convolution. F epsilon of x is equal to eta epsilon convolved with f tilde of x, our continuous extension of f. Now, I claim that this function is actually infinitely differentiable. You can see that this integral here depends on y, okay? And all of the x dependence of our convolution is pushed onto the smooth bump function, like so. You can see the only x dependence shows up in eta epsilon in the integrand. So when I take the derivative of this function on the outside here, by the Lebesgue-dominated convergence, that derivative can be pulled inside of the integral. And I can apply it, it's a derivative with respect to x, I can apply it to our smooth bump function, which is infinitely differentiable. So I can take as many orders of derivatives as I want of f epsilon of x. It will be well defined, despite the fact that f tilde might be a monstrosity and completely not differentiable. Okay, so this is already a huge step because we've now constructed a smooth function which is a convolution of f tilde by eta epsilon, by a smooth bump function, and we're claiming that for epsilon small enough, okay, this is actually going to be our desired approximation. So let's look at why this is the case. If you let x be in k, okay, notice that the support of eta epsilon is going to be, in this form, it's going to be a ball centered at x of radius epsilon, which for the proof, in our case, we're actually going to choose this to be f delta, okay, so picture an f delta in your mind. So the support of eta delta here is going to be a ball centered at x of radius delta, which means that if x is in k, then the support of these eta epsilons are always going to be contained in this k delta here, which is a fattening of k of width delta. So basically, I'm defining k delta to be the set of all y in Rn such that the distance from x to y is less than delta for some x in k. Now this set just fattens k a little bit by delta. It's still closed and it's still bounded. Essentially, by the definition here, we have a less than or equal symbol to ensure that it's closed, and it's certainly bounded because k is bounded. So therefore, it's compact because in Rn, closed and boundedness is sufficient for compactness. Now, f tilde is uniformly continuous on k delta because it's continuous, and k delta is a compact set. Therefore, by uniform continuity, for an epsilon greater than 0, we can choose a delta greater than 0 such that for all x and y in k delta, x minus y less than delta implies that the distance from f tilde of x to f tilde of y is less than epsilon. Great, this is just the definition of uniform continuity. Now, let's see that if we take f delta to be our desired Weierstrass approximation, then we're going to get that the distance, let's go to the next slide here. The distance between f delta of x and f tilde of x is going to be less than epsilon. Okay, so let x be in k once again, and let's unpack this left-hand side. Okay, so the distance between our approximation function and f tilde of x is equal to the integral over Rn of the convolution function eta delta of x minus y multiplied by f tilde of y minus f tilde of x. Now this is kind of a trick being employed here, okay? Basically, I've unpacked the definition of f delta, and then I've brought f tilde of x, I've written f tilde of x as actually the integral of eta delta of x minus y f of x dy. This is because x is a constant, f of x is a constant with respect to the integration variable y, okay? And the integral of eta x minus y dy is just 1, so I can multiply by 1 and multiply by this integral, and then bring f of x inside of the integral because it's a constant with respect to y. Once you do that and you write out the definition of f delta of tilde, you're going to get, once you bring the two integrals together, you're going to get this expression here, okay? The next step is we recognize by our construction of k delta, again, the support of eta delta of x minus y, no matter what x is always going to be contained in k delta. Therefore, since eta delta is 0 outside of k delta, we might as well just choose the integral to be over k delta, and that's this next step here. Finally, we use the triangle inequality for integrals, which says that I can bring the absolute value inside of the sum and bound it above. Okay, so that's just the triangle inequality for integrals here. Now finally, I use the fact that we have uniform continuity of f tilde, so this term f tilde of y minus f tilde of x is bounded above by epsilon, and then I bound it above by epsilon, bring it outside of the integral, I'm left with an integral of our bump function over its support, which is just going to be 1, okay, and so I'm left with epsilon. And so this proves that indeed f delta is our desired approximation function because for all x and k, the distance between f delta of x and f tilde of x is less than epsilon. Okay, here are some references. Specifically, this Evans book is where you can find the this first, the notation and where I got this smooth bump function from. Now, all these other references were kind of used in my proof of the Schauder and Brouwer fixed point theorems in a previous video. And the reason why I called this a lemma here, it's certainly not just a lemma, it's definitely a theorem, but it's called a lemma because it's used in the proof of the Brouwer fixed point theorem in order to approximate a continuous map with a differentiable map. And that's just one of a literal ocean of applications for this theorem. I mean, it's really hard to understate. So let me just erase this little pen mark here and let you meditate on the statement of this theorem for a little while.